Hello friends, in this video I'm going to discuss Maclaurin's power series for given functions. Okay, let us start. Let a function f possesses continuous derivatives of all orders in the interval close interval 0x. So that we have from Maclaurin's theorem f has continuous derivatives of all orders in close interval 0x. Then from Maclaurin's theorem we have f of x is equal to f of 0 plus x into f dash 0 up to xn minus 1 divided by n minus 1 into f n minus 1 0 n minus 1th derivative of f at x is equal to 0 plus Rn, where Rn denotes a remainder after n terms. Okay, this we know from Maclaurin's theorem. Now let us assume that Sn is equal to f0 plus xf dash 0 up to xn minus 1 divided by n minus 1 factorial into fn minus 1 0. So that fx is equal to Sn plus Rn. Okay, then fx is equal to Sn plus Rn. Now Rn tends to 0 as n tends to infinity if and only if fx is equal to limit n tending to infinity Sn. Now fx is equal to Sn plus Rn. Now taking limit as n tends to infinity, Rn tends to 0 as n tends to infinity if and only if fx is equal to limit n tending to infinity Sn. Clear from this? Okay. Next, we have the statement. Therefore, we have the following. If if f possesses continuous derivatives of all orders in closed interval 0x. Second is Rn, remainder after n terms, whether it is Cauchy form of remainder or Lagrange's form of remainder, tends to 0 as n tends to infinity. Then we have this fx is equal to f0 plus x into f dash 0 plus xn upon n factorial fn 0 up to so and so. Okay, this series is known as Maclaurin's infinite series for the expansion of fx as power series. Okay, this is Maclaurin's infinite series. Okay, means if we have a function satisfying these two conditions, f is continuous derivatives of all orders in the closed interval 0x and remainder after n terms tends to 0 as n tends to infinity, then we have this Maclaurin's power series, Maclaurin's infinite series for the expansion of fx as power series. Okay, clear? Now we shall obtain the Maclaurin's expansion of ex, sin x, cos x, 1 plus x power m, where m is a real number, and log 1 plus x. Okay, now let us start one by one. Now first we obtain the expansion of exponential x, ex. Okay, now let fx is equal to ex, so that nth derivative will be ex only. Okay, and fn0 is e0 is equal to 1 for every n belonging to n. Clearly, f and all its derivatives exist and are continuous. Exist and are continuous for every real value of x. Okay. Now, Lagrange's form of remainder. We have to show Rn tends to 0 as n tends to infinity. This is second condition. Okay, first condition holds. Now we have to show the second condition. Rn remainder tends to 0 as n tends to infinity. Now, Lagrange's form of remainder. Lagrange's form of remainder. Now, Lagrange's form of remainder is Rn is equal to xn by n factorial fn theta x, where theta lies between 0 and 1. That means from here, this is xn by n factorial e theta x. Okay. Now we have to show this Rn tends to 0. To show this tends to 0 as n tends to infinity. To show. Okay. Now for this, we will use a result, and the statement of the result is, we will use this result if an denotes, the nth term of the series an, and if limit n tending to infinity an plus 1, where an plus 1 is the n plus 1th term of the series, this divided by an is equal to L, where mod L is less than 1, then limit n tending to infinity an is equal to 0. This result we are going to use in this. Okay, if an denotes the nth term of the series this, and an plus 1 is the n plus 1th term, and limit an plus 1 divided by an is L, where mod L is less than 1, then this limit is equal to 0. Okay, now we are going to use this result in this particular expansion of exponential. Okay, now here we have Rn is equal to xn by n factorial e theta x. Now let an is equal to xn by n factorial for every n belonging to capital N. Then an plus 1 will be x power n plus 1 divided by n plus 1 factorial. Then limit n tending to infinity an plus 1 divided by an will be limit n tending to infinity xn plus 1 x power n plus 1 divided by n plus 1 factorial into n factorial divided by xn. That is, this is limit n tending to infinity x divided by, this will be n plus 1 into n factorial, n plus 1, and on taking limit this will be 0 as n tends to infinity, which is clearly less than 1. Therefore, from this result we get limit n tending to infinity an is equal to 0. That is, limit n tending to infinity xn by n factorial is equal to 0. Okay, now limit n tending to infinity Rn is equal to limit n tending to infinity xn by n factorial e theta x. This is limit n tending to infinity xn by n factorial into e theta x, that is 0 into e theta x is equal to 0. That means second condition is also satisfied. Therefore, both the conditions of Maclaurin's theorem, Maclaurin's expansion is verified. That means, therefore, the conditions of Maclaurin's infinite expansion are satisfied. Therefore, for every x belonging to R, Ex is equal to Fx has the form f0 plus x f dash 0 plus x squared by 2 factorial f double dash 0 plus xn by n factorial fn 0, and this series is infinite. That means this is equal to 1 plus x square by 2 factorial up to xn by n factorial and so on. That is, this can be written as xn by n factorial and running from 0 to infinity. Okay, clear? This is expansion of Ex. Next, we will find the expansion of Sine X. Okay. Now, let fx is equal to Sine X. Then, any derivative fn x will be sine n pi by 2 plus x, that we know from any derivative topic. Okay. Now, fn 0 will be sine n pi by 2 for every n in n. Okay. Now, this is fn 0 is sine n pi by 2 where n is a natural number. Okay. Now, if I take n to be 1, then f dash 0 will be, if I take n to be 1, sine pi by 2, that is 1. If I take n to be 2, then this is sine 2 pi by 2, that is sine pi, that is, this will be 0. If n is 3, fn 0 will be sine 3 pi by 2, that is, this will be minus 1. For n is equal to 4, fn 0 will be 4 2 pi, that is 0 only. Therefore fn 0 can be written as, it is 0 if n is even and it is minus 1 power n minus 2 if n is odd. Okay, we can write fn 0 in this form. Now clearly f and all its derivatives exist and are continuous for every real value of x. For every real value of x. Now second condition is we have to show remainder tends to 0. Now we consider Lagrange's form of remainder. Which is Rn is equal to xn by n factorial fn theta x, where theta lies between 0 and 1. Next condition is this, we have to show Rn tends to 0 as n tends to infinity. Okay. Now Rn is equal to xn by n factorial and fn theta x will be sine n pi by 2 plus theta x. We have to show this tends to 0 as n tends to infinity. This we have to show. Okay. Now we have this xn by n factorial sine n pi by 2 plus theta x. This is xn by n factorial sine n pi by 2 plus theta x. Now clearly this is less than or equal to mod xn by n factorial, since sine n pi by 2 plus theta x is less than or equal to 1. Okay. Now from previous expansion of exponential x, we know limit n tending to infinity xn by n factorial is equal to 0 for every x belonging to R. Therefore, limit n tending to infinity mod Rn is 0, and hence limit Rn is equal to 0 as n tends to infinity. Okay, therefore conditions of Maclaurin's infinite expansion are satisfied. Clear? Therefore, for every x belonging to R, we have sin x is equal to f0 plus x f dash 0 plus x square by 2 factorial f double dash 0 xn by n factorial fn 0 and so on. Okay, now substituting the values of f0 f dash 0 in this, we have this sin x is equal to fx is f0 is x. Okay, now f0 is 0, f dash is x, f dash 0 is x minus x cube by 3 factorial, okay, plus x5 by 5 factorial, and this is expansion of sin x. On substituting values of f0, which is 0, x f dash 0, x square by 2 factorial, f double dash 0, which is again 0, f double dash 0, and on substituting these values, we have this expansion. Okay, now similarly expansion of cos x. Similarly, we can easily find the expansion of cos x as, it can be easily found, cos x expansion is 1 minus x square by 2 factorial plus x4 by 4 factorial. This is the expansion of cos x. Okay. Next, we will find the expansion of 1 plus x power m, where m is a real number. Okay, now we will find the expansion of this. Okay, here we will consider two separate cases. First, when m is a positive integer. Next, when m is not a positive integer. Okay, now two cases arise according as m is positive, m is or not a positive integer. M is or not a positive integer. Okay. First, we consider the case when m is a positive integer. When m is a positive integer. First, we consider this case when m is a positive integer. Okay. Now, let fx is equal to 1 plus x power m, where x belongs to R. Okay. Next, we consider this. Then, fn x exists for all x and for all m. Okay. Now, if if 1 less than equal to n less than equal to m, then nth derivative of this fx is given by, if n lies between 1 and m, then nth derivative is given by fn x is equal to, then fn x is equal to, then fn x is equal to, this is nth derivative, fn x is equal to m into m minus 1 into m minus 2 up to m minus n plus 1 plus x power m minus n. Okay, so that This is nth derivative of 1 plus x power m. Okay, so that, and we have this f of fmx. Now taking n to be m here, we have m into m minus 1, m minus 2, up to m minus m plus 1, 1 plus x power m minus m. That is, this is 1, that is m factorial. This is 1 plus x power 0, that is 1 only. Okay, and fn x is equal to 0 if n is greater than m. Since the power of this 1 plus x power m. Okay, we have this fx, and when n is greater than m, then n derivative will be 0. It is clear? Okay. Therefore, we have this fn x, fn 0 is equal to, is given by m into m minus 1, m minus 2, up to m minus n plus 1 if n lies between 1 and m, and it is 0 if n is greater than m. Okay, this is fn 0. Okay, now since from this we see that since fn x is equal to 0 for all n greater than m, and we have to show, we want to show Rn tends to 0 as n tends to infinity, and Rn is xn by n factorial fn theta x. Okay, that we want to show. As n tends to infinity, this tends to 0. Okay, now here, as n is greater than m, for n greater than m, we have fn 0 is 0 only. Okay, that means Rn tends to 0. It follows that Rn tends to 0 as n tends to infinity. Okay, from here, after m plus 1, from m plus 1 onwards, all derivatives are 0. Okay, that means Rn tends to 0 as n tends to infinity. That means conditions of Maclaurin's expansion is satisfied. Okay, therefore we can say, therefore the conditions of Maclaurin's expansion, Maclaurin's expansion are satisfied. Okay, therefore we have this 1 plus x power m, which is our fx, is equal to f0 plus x f dash 0 up to xm upon m factorial fm0. Okay, no terms after this, since derivative is 0 after m plus 1, from m plus 1 onwards. Okay, that means this is 1 plus mx plus m into m minus 1 by 2 factorial x square up to xm. Okay, this is our first case. Next, we consider the case when m is not a positive integer. M is a real number, but it is not a positive integer. Okay, when m is not a positive integer. Okay, next we consider this case when m is not a positive integer. Now let fx is equal to 1 plus x power m, where x is not equal to minus 1. Okay, clear? Since m is not a positive integer, if x is equal to minus 1, then x is equal to minus 1, this will be 0. X is not equal to minus 1 here. Okay, now taking here, we will consider Cauchy form of integer. Okay, not Lagrange's form of remainder, since it is not possible to show Rn tends to 0 as n tends to infinity in case we consider Lagrange's form of remainder. For this particular case, when m is not a positive integer, we have to consider Cauchy form of remainder. Taking Cauchy form of remainder, we have Rn is equal to xn upon n minus 1 factorial 1 minus theta n minus 1 fn theta x, where theta lies between 0 and 1. Okay, we consider this. Therefore, Rn will be equal to xn by n minus 1 factorial into 1 minus theta power n minus 1 into m minus 1 up to m minus n plus 1 into 1 plus theta x power m minus n. Okay, now this is equal to m into m minus 1 up to m minus n plus 1 into xn divided by n minus 1 factorial into 1 minus theta 1 plus theta x power n minus 1 into 1 plus theta x power m minus 1, since m minus n minus 1 minus n is m minus 1. Therefore, power is m minus 1 here. Okay. Now, next, we will show this tends to 0 as n tends to infinity. Then this term tends to 0 as n tends to infinity. And this term also tends to 0 as n tends to infinity. Individually, we consider these three terms and will show it's tend to n tends to, as n tends to infinity, this term tends to 0. Okay. Now, first we consider this term. Okay. Now let an is equal to m into m minus 1 up to m minus n plus 1 divided by n minus 1 factorial xn. Then an plus 1 will be m into m minus 1 m minus n plus 1 m minus n divided by n factorial into x power n plus 1. Okay. Now, therefore, an plus 1 divided by an will be m into m minus 1 up to m minus n plus 1 m minus n upon n factorial. This is xn plus 1 into n minus 1 factorial divided by m into m minus 1 up to m minus n plus 1 into xn. Okay, clear? Now, this will get cancelled out. And this is n into, this can be written as n into n minus 1 factorial. And this is x into x power n. Okay. That means on simplifying we get this is equal to, this Rn is equal to, m minus n divided by n into x. That is, this is m by n minus 1 into x. Now, on taking limit as n tends to infinity, an plus 1 divided by an is equal to limit n tending to infinity, m by n minus 1 into x. That is, this is equal to minus x. This will be 0 and we are left with minus x. That means it follows that if this is less than 1, then limit n tending to infinity, an is equal to 0. This implies m into m minus 1 up to m minus n plus 1 divided by n minus 1 factorial into xn tends to 0 as n tends to infinity for mod x less than 1. Okay, mark this as 1. Okay, now we will consider the second part, which is 1 minus theta by 1 plus theta x. Okay, now for this we start with, since theta lies between 0 and 1, and now minus 1 less than x less than 1, x lies between this, therefore from this minus theta less than theta x less than theta, multiplying by theta here, and now adding 1. Okay, now this is 0 less than 1 minus theta less than 1 plus theta x. Since theta lies between 0 and 1, 1 minus theta is positive, therefore we have this. Okay, and from this we get 1 minus theta by 1 plus theta x lies between 0 and 1. Okay, now on dividing by 1 plus theta x here, on dividing by 1 plus theta x here, we have this. That means we have this. This implies 0 less than 1 minus theta divided by 1 plus theta x less than 1. That means this lies between 0 and 1. This means limit n tending to infinity 1 minus theta 1 plus theta x power n minus 1 is equal to 0 as n tends to infinity. Since this lies between 0 and 1 and its power is n minus 1, and when n tends to infinity, this will be 0. This is very small number lying between 0 and 1. On taking limit, this will be 0. Okay, now second one is also 0 as n tends to infinity. Now we consider third part, that is 1 plus theta x power m minus 1. Okay, now we have this, and theta lies between 0 and 1. Okay, now in this multiply theta here. This is, we have this, clear? That means we have this, we have this. Okay, which is less than mod x. We have this expression, this inequality, sorry. Now here adding 1 we get adding 1 here, we have this. Okay, now if m is greater than 1, if m is greater than 1, then 1 plus theta x power m minus 1 will be less than 1 plus mod x power m minus 1 from here. Okay, and if m minus 1, if m is less than 1, that is m minus 1 will be less than 0 in this case, and here m is greater than 1, that means m minus 1 is greater than 0. If m is greater than 1, then m minus 1 is greater than 0, we have this. And if m is less than 1, then we have this, m minus 1 is less than 0. Then 1 plus theta x power m minus 1, which is equal to 1 upon 1 plus theta x power 1 minus m. Okay, and this will be less than 1 upon 1 minus mod x power, sorry, here, from here we are taking 1 minus mod x is less than 1 plus theta x is less than 1 plus mod x. Okay, we are considering two separate cases. When m is greater than 1, that means m minus 1 is positive. That means we have 1 plus theta x power m minus 1 is less than 1 plus mod x power m minus 1. And second, when m is less than 1, that is m minus 1 is less than 0. Now we will consider this case. Okay. This will be 1 plus theta x. This will be less than 1 minus mod x power 1 minus m. Okay. Or this is 1 minus mod x power m minus 1. Okay. Now mark this as equation number. Mark this as equation number 3. Okay. This 1 plus theta x power m minus 1 is less than 1 plus mod x power m minus 1. If m is greater than 1 and if m is less than 1, then 1 plus theta x power m minus 1 is less than this. Okay. Now from 1, 2 and 3, from 1, 2 and 3, from all these three cases, we have from 1, 2 and 3, we have from 1, 2 and 3, we have for mod x less than 1, limit n tending to infinity, Rn is equal to 0. Therefore, the conditions of Maclaurin's expansion, Maclaurin's infinite expansion are satisfied. Therefore, we have 1 plus x power m is equal to fx is equal to f0 plus x f dash 0 up to xn by n factorial fn 0 and so on. That is this m minus 1 by 2 factorial x square up to x m into m minus 1 up to m minus n plus 1 divided by n factorial xn n dash. This is infinite expansion of 1 plus x power m when m is not a positive integer. Okay, clear? Now we will find the expansion of 1 plus x. We will find the expansion of log 1 plus x. Okay, now we will find the expansion of this. Now let fx is equal to log 1 plus x, where 1 plus x is positive, that is x is greater than minus 1. Okay. Now we know from nth derivative formula, if y is equal to log ax plus b, then yn is equal to minus 1 power n minus 1 into n minus 1 factorial divided by ax plus b power n into an. We have this nth derivative. Now here we have a is 1 and b is 1. Okay. Therefore, fn x is equal to minus 1 power n minus 1 into n minus 1 factorial divided by 1 plus x power n and 1 power n. A is 1 here for every n in n and x greater than minus 1. Okay, this is fn x. Now we will consider first case when x lies between 0 and 1. We will consider this case. Now, Lagrange's form of remainder. We have to show Rn tends to 0 as n tends to infinity. Okay, Rn is xn by n factorial fn theta x, where theta lies between 0 and 1. Okay, now this is equal to xn by n factorial, and fn is minus 1 power n minus 1, n minus 1 factorial, 1 plus theta x power n. Okay, this is now this is equal to minus 1 power n minus 1 divided by n into x by 1 plus theta x power n. Okay, this is Rn. Now, if x is equal to 1, if our x is equal to 1, then mod Rn is equal to 1 upon n. This is positive. This is equal to 1 upon 1 plus theta power n, and it is less than 1 by n. Clear? Since theta is greater than 1, theta lies between 0 and 1, and here 1 plus theta is clearly greater than 1. That means 1 upon 1 plus theta will be less than 1, and therefore 1 plus theta power n into 1 by n will be less than n, 1 upon n. Okay, this is clear. Since denominator is more than numerator, we have this, and here we have this. Okay, now also 1 upon n tends to 0 as n tends to infinity. Therefore, we have limit n tending to infinity, Rn is equal to 0. Okay, for the case when x is equal to 1. Now, if x lies between 0 and strictly less than 1, since we have already considered the case when x is equal to 1 here. Okay, next we consider this case when x is strictly less than 1. Okay, now then, since theta lies between 0 and 1, this implies we have this on multiplying by x, and on adding 1 we have this inequality. Okay, now next we have this, therefore we have 0 less than equal to x less than 1 less than 1 plus theta x, that is 0 less than x less than 1 plus theta x. Clear? Now this implies 0 is less than x by 1 plus theta x less than 1. Okay, now dividing by 1 plus theta x, and this is equal to, this will imply 0 less than x by 1 plus theta x less than 1. Okay, clear? Since this number, this lies between 0 and 1, power will also lie between 0 and 1 only. Therefore, we have this x 1 upon 1 plus theta x power n is less than 1 by n, and therefore since 1 by n tends to 0 as n tends to infinity, we have limit Rn is equal to 0 as n tends to infinity. Okay, clear? For the case when x lies between 0 and 1. Okay, now we consider the second case when minus 1 less than x less than 0. Okay, we consider this case. Now we have this, since in this case since in this case x by 1 plus theta x need not be less than unity, where theta lies between 0 and 1 and x lies between minus 1 and 0. That means this need not be less than unity. Okay, therefore it may not be easily shown that Rn tends to 0 as n tends to infinity by considering Lagrange's form of remainder. Therefore, we will consider Cauchy form of remainder here. Okay. In this particular case, we will consider Cauchy form of remainder. Okay. Now, Cauchy form of remainder. Writing Cauchy form of remainder. After n terms. We have Rn is equal to xn by n minus 1 factorial 1 minus theta power n minus 1 fn theta x, where theta lies between 0 and 1. Okay. Now here we have xn by n minus 1 factorial 1 minus theta power n minus 1, and here we have this divided by 1 plus theta x power n. Okay. Now this is 1 minus theta 1 plus theta x power n minus 1 upon 1 plus theta x. Okay. This is Rn. Now this Rn, and this we have to show tends to 0 as n tends to infinity. That we have to show. Okay. Now x lies between minus 1 and 0 and theta lies between 0 and 1. That we know. From here we get 1 minus theta is positive. Okay. This implies minus theta is less than theta x. From here, that means 1 minus theta is less than 1 plus theta x. That is 0 less than 1 minus theta is less than 1 plus theta x. Clear? Okay. That means this is equal to 0 less than 1 minus theta less than divided by 1 plus theta x lies between 0 and 1. Mark this as equation number 1. Okay, clear? Now, also we have this less than equal to x. This means minus theta mod x is less than equal to theta x. Clear? Okay. Now, since 0 less than theta less than 1, we have minus theta. This minus theta into mod x is greater than minus mod x. Okay. Therefore, minus mod x is less than minus theta mod x is less than or equal to theta x. This implies 1 minus mod x is less than 1 plus theta x. From this adding 1. Okay. Now this implies 1 upon 1 minus mod x is greater than 1 upon 1 plus theta x. Okay. That is 1 by 1 plus theta x is less than 1 by 1 minus mod x. Mark this as equation number 2. Now therefore mod Rn is equal to mod xn 1 minus theta by 1 plus theta x power n minus 1 into mod of 1 upon 1 plus theta x. Okay, and this is less than mod x power n upon 1 minus mod x using equation numbers 1 and 2. Okay, now mod xn tends to 0 as n tends to infinity. Since mod x is less than 1, okay, mod x is less than 1, therefore limit n tending to infinity Rn is equal to 0. That is clear. Now therefore we find that therefore we find that if minus 1 less than x less than or equal to 1, then limit n tending to infinity Rn is equal to 0. Therefore both the conditions of Maclaurin's infinite expansion are satisfied. Therefore we have log 1 plus x is equal to fx is equal to f0 plus x f dash 0 plus x square by 2 factorial f double dash 0, and this is x minus x square by 2 plus x3 by 3 and so on. Okay, now that's it for this video. If you have any queries or any suggestions, please write to me in comment box. Thank you.